is going to talk about mathematical and statistical insights into gut Microbiota-Phytocannabinoid-Diet Interplay in Murine Prostate. And I hope I didn't butcher it too much. And you can see the timer right there, right? Yes. Okay, off to you.
Okay, hello everybody, and it's almost scary to be the first talk today. So it's great to have the opportunity to talk about my research. That's only part of it, but I chose this particular study because I thought it's a very good example of interdisciplinary collaboration and of how mathematics, statistics, and machine learning can together support also other disciplines, and in this particular case is research in oncology. And as you can see, it's a collaborative work with groups from Professor Ronca, Professor Ligressi, who are experimentalists, but also Joe Starkey, who's doing his PhD here at Sussex, has been doing some work on it, and Lon Monaghan, who was a very successful master student on our data science course. So the study wanted to understand the effects of different types of drugs and diets on the development of prostate cancer. And for this reason, we consider some genetically modified mice. These are called Trump mice that develop cancer at around week 7, 8 in their lives. And by week 12, the cancer is visible. By week 25, the mice are sacrificed. And so you can measure things like a prostate weight and also see the severity of the cancer and so forth. We also collected feces to understand how gut microbiome changes in time and how it changes with these different treatments. I have to say, though, that this experimental design that looks amazing on paper, unfortunately, had a problem towards the end because they forgot to collect the feces of the mice at 25 weeks when they were on regular diet. So the first analysis showed that a high-fat diet had a very big impact on prostate cancer development, and that the drugs had a different effect on the mice that were on the two different diets. We also saw that we could quite nicely separate those mice that were under a particular drug called enzalutamide from the other mice. You can see the two nice groups. And a bit more, we could say, for example, that this combination, CBD-CBG, was much more effective on high-fat diets than the other ones. So through a random forest, we put all our covariates together. So we consider gut microbiome and the physiology measurements. And so we were able to identify some predictors, and in particular, a couple of genera that seem to be very good candidates to understand how severe the cancer is. And of all the physiology measurements, instead, the only thing that seemed to have some use was the prostate to body weight. As I said, we were missing a control at 25 weeks for regular diet mice. And I don't know how much you know about gut microbiome, but you can't just do new experiments and use those experiments with the previous ones you had. And so what I proposed instead was to use maths. Okay, so as I said, maths, stats, ML, for me, they are all a bit together, let's say, in my research right now. And the idea was to have new experiments that we would grow these mice for 25 weeks, and we would analyze the gut microbiome, so to build like a time series of the gut microbiome, and then use a mathematical model based on this data to obtain a control at 25 weeks for our initial data. And so this is what we did. We also, in this case, we consider not just from mice, also wild type, because once you do an experiment, you can say, okay, let me also see if the genetics plays a role, okay, and how different the gut microbiome is. And it was very interesting to see that there is a difference, but only in the early stages of the development of the mice. Okay, once they become adults, you can't see that difference anymore. So, of course, to use a mathematical model to create this control, we wanted to be sure that we could say something about this time series, in particular, that there was somehow some correlations between what was happening at each step. So we looked if somehow you can predict at each time step what is going to happen by using what you had at the previous steps. We also saw that we could again distinguish quite well between Trump mice and wild-type mice, and that was especially true for some of the family of bacteria. Through this analysis, we were also able to identify 4 families that have a completely opposite behaviors in the 2 types of mice, so in the 2 genotypes. And again, these could be considered as possible markers to understand the severity or to track the severity of the prostate cancer. Okay, so we were quite satisfied with what we obtained before. And so we said, okay, then we can actually develop this mathematical model and then use this mathematical model by considering a week 12 of the previous experiments as our starting point. And so we develop, in this case, we create this control at 25 weeks. And so once we had that, then we could compare what really was happening at 25 weeks between regular diet and high-fat diet. And it was quite amazing to observe how completely different the 2 diets, the effect of the 2 diets on the gut microbiome. And so you can see that the diversity, in particular, the diversity of these bacteria populations is completely different. Okay, the high-fat diet reduces strongly and in a very significant way the diversity of the gut microbiome. Finally, the models allowed us to say a bit more also about the networks of in the gut microbiome, so these networks of bacteria. And we could see that actually what the therapies really do, the drug therapies, is to increase the stability of the system. Okay, so which means to make the system more resilient to external changes. And this seems to be a way of going towards a cure, let's say. So the more stable the system is, the healthier is the mouse, which is something we couldn't find anywhere else in any other study. Okay, so these are then my conclusions, almost perfect. So you can see that we found out, yes, a high-fat diet makes prostate cancer worse. We were able to identify combined treatments that have an effect on gut microbiome, but also on the severity of the cancer. So it improves somehow the situation of the mice. So it's a possible cure, or could be eventually. And finally, we could see that actually single treatments didn't have any effect, but it's something probably many people know already, that in cancer you need combination of drugs. And that's all for me. Thank you very much. And if you have any questions.
Yeah, perfect. So we have time for questions. I was going to
I have a quick one. Out of interest, the mice that you used in your experiments, were they like lifelong vegetarians or meat eaters, or did they have like, mapping this to population of humans, say, where most people eat too fatty and then need to change their diet? So how was it in your?
So the diets were, I mean, I don't think it's a vegetarian and meaty kind of thing. It's more that they were given more fats and sugars in the high-fat diet mice.
From the start, or were they kind of eating unhealthy and then change?
No, from week 4.
From week 4.
Yeah. So up to week 4, as babies, they were given the same diet, and then they would change that. Yeah.
Thanks for a really interesting talk. So do you think the gut microbiome change causes the cancer or comes as a side effect of the cancer?
That's a very good question. I don't think it goes only in one direction. I think, yes, I think the cancer definitely, well, the development, I mean, this is what the experiments show, the development of the cancer causes a change in the gut microbiome. But once the cancer is there, you don't really see those changes anymore. And the drugs has an effect on the gut microbiome, but it seems that to stabilize the gut microbiome also brings a positive effect onto the cancer. So it's a two-way.
Really, it's a sign of causality going from the microbiome to the cancer.
Well, before talking about causality, I would be very careful, but it seems that there is a double direction there.
Yeah. I was definitely getting this exercise today.
Thanks for the talk. It was really interesting. Sorry if I missed it, but did you test your time series for stationarity?
We did test, yes, and they were neutrally stable. So I could have forced stability, but to force stability in this type of model, it means that then you force everything to go to zero asymptotically, and that wouldn't make much sense if I wanted to build a control at the end. So, and also, who says that the systems has to be stable rather than neutrally stable?
Yeah, I wasn't arguing that it needs to be. It's just.
I mean, I'm saying because actually that was something I really thought about. I tried both ways. And I went for keeping the stationarity as it was, which is this one. I mean, you can see the two maximum eigenvalues there. Yeah.
Okay, thanks.
Okay, yeah, then thank you very much, Marianna.
Yeah.